Search Algorithms by Grupo C. Written by Manuel Alejandro Umaña Rodriguez, Dahyna Martínez Pérez, Luis PEREZ-DEJESUS, and Christopher Hans Mayens Matías. The agenda includes purpose of experiment, hypothesis, concepts, experiment setup, information, conclusion, and credits and references. Purpose of experiment. How does a well-developed scenario can help identify which algorithm is required to solve a problem? How effective are different algorithms at solving the problem statements based on the constraints of the problem and any hint that may be given? Key questions and hypotheses. The key question is, does the design of a problem affect the type of search algorithm selection? Hypothesis. If the design specifications and constraints of a problem are properly set, the type of search algorithm required to solve the problem can be chosen with more precision.
Concepts, experimental concepts, platform, Python programming language of high level, emphasis code readability with the use of indentation. Subject, the agent's ability to effectively find its path, overcoming obstacles and restrictions. Measure, the amount of steps it takes the agent to reach the goal saved from the initial state. Experiment setup, tools and resources utilized. We use the AIM code repository, the core repository containing fundamental code and algorithms for both problems. For problem 3.7, the A** and greedy BFS algorithms were used for testing as well as the straight line distance heuristics. For problem 3.9, the breadth first search and the depth first search were used for testing with the solution being found, which BFS as DFS could not find that solution. Method for comparing. For problem 3.7, the criteria used for comparison was the shortest path between algorithms. The shortest path was determined by counting the number of states or steps visited from the starting position to the goal state. For problem 3.9, comparison was the amount of steps to find the solution. The amount of steps for the algorithm took determined the efficiency when finding the goal state.
Information. This figure represents the original state for the 3.7 problem, which is an environment with several obstacles that are represented here by different shapes. And this is the base state for all of the experiments with exercise 3.7. Here's the first case. We decided to make the start and the goal adjacent to each other. It's like similar to the first figure. Here it's better represented without the numbers, so it's clearer to view. And here is the solution using the A* algorithm. Here's the solution using the greedy best first search algorithm. And this is the second case, which is basically a sort of direct line between the start and the goal, only a small obstacle at the end. Here's the solution with the A* algorithm, and here's a solution with the greedy best first search algorithm. This is the third case, which is sort of an inconvenient case, a case where the start is between two roads and the goal is hidden behind a corner of a figure. Here's the solution for the A*, and here's the solution for the greedy best first search algorithm.
Figure 12. Complete state for ballot moves in missionaries and cannibals problem. Figure 13. Optimal solution found for the missionaries and cannibals problem by breadth first search. Conclusions and lessons learned. Number 1. Heuristic function utility. Informed search algorithms require informed about environment. Heuristic function estimates the cost from the current position to the goal. There is an efficient way for a search algorithm to traverse from point A to point B. Having additional information like cost and start to the current position significantly reduces the amount of mistakes the agent can make. Speed versus optimality. Having additional information makes the code optimal, but also adds complexity. An increase in complexity decreases the speed because it makes the agent analyze more data before making a decision. Understanding which search algorithm you utilize in a specific environment is key to finding the best solution. Number 3. Problem formulation. By formulating the problem definition correctly, it is possible to find the most appropriate, uninformed algorithm for the task at hand. Number 4. Choosing the best algorithm in uninformed algorithms. Based on provided information, some problems may prefer certain responses depending on the length of the search or the memory constraints. Uninformed algorithms may be more suited for environments where there are not many variables affecting the agent or unknowns. Credits and references.